All right. So what we are talking about today is alkene chemistry, and there's a couple of vocab terms that we have to go through first, and then I'll show you how we can tackle this unit in a very, very simple way. And we're going to be covering the usual reactions that are in uh, this kind of unit that show up in a lot of different places and different schools. And then in another video, we'll go over some of the more fringe reactions and how they fit into other stuff. So as always, we are talking about alkene chemistry. All right. Now, what I want you to know is that we're starting off and we're talking about a carbon-carbon double bond, right? And what this means is that we essentially have two different carbons that are completely different from each other, right? This one's on the left, that one's on the right. And depending on the uh, kind of double bond that we can have very different kinds of carbons involved in this carbon-carbon double bond. So let's take a look at these two examples. The first example here with what we notice is that we have a tri-substituted alkene, meaning that we have three things bonded to the carbons involved in the carbon-carbon double bond that are not hydrogen. And what we see is that these are unequal, right? That we have a less substituted side and we have a more substituted side, right? And we can see that this only has one substitution and that has two substitutions. When we take a look at this example over here, we can see that, okay, we have two carbons involved in a carbon-carbon double bond, but they are equally substituted. That this has one substituted and this is one substituted. So we can't say that there is a more or less substitution, they're just equal. Another example that we can talk about is something like that, where once again, we look at the two carbons involved in the carbon-carbon double bond and we can say, okay, neither one of these is more substituted than the other. However, what happens if I tack on a nice alkyl chain there? Or what happens if I put an OH there? How does this change the nature of our more or less substituted sides or equally substituted? Well, if we look over here, we can say, okay, well now this red carbon has two substitutions, right? One, two. And if we look over here, this only has one substitution. So now we have a less and a more substituted side. It does not matter what those substitutions are. It only matters if they're physically there attached to that carbon, okay? If we take a look at what's going on over here, what we notice is that we have one, two substitutions, one, two substitutions. Well, doesn't it matter that this thing is bigger and, wild? And, what happens if this has like a chlorine on it? Maybe it connects into this ring, stuff like that. Does this matter? No, it does not. Okay. The fact that there are two substitutions, it doesn't matter if one of them is big, complicated, gets in the way, doesn't matter at all. This is equally substituted. Okay. And this is going to come into a part because we're going to talk about a kind of reaction type called Zaitsev, which is named after a guy who did a lot of work with these, not Zaitsev, whoops, my bad, Markovnikov, different Russian scientist, Markovnikov. And what Markovnikov did is he came up with a rule, and he said that some reactions, a Markovnikov reaction will favor the more substituted side. All right. And so this idea of more or less substituted is going to be a very, very important thing when we're talking about this. Now, there's a couple of other vocab words that we have to talk about that, and it's regioselectivity and stereoselectivity. Okay. Regioselectivity is basically like saying which carbon are we choosing? Which carbon are we choosing? Okay. And what I mean by that is that sometimes when we do alkene chemistry, what we're going to find is we're adding a bond into the double bond. We're going to destroy it. We're going to go over this. It's going to make a total bunch of sense. But when we're talking about regioselectivity, we're talking about which carbon. And again, this falls into this idea of Markovnikov. So, we're talking about more or less substitution, stuff like that. So more, less substituted carbon. And so if you're thinking, does regioselectivity, is this an umbrella term? Yes, it is. And what is underneath this umbrella term is Markovnikov. So Markovnikov is uh, a type of regioselectivity. All right. The second kind of vocab word that we're going to be talking about is stereoselectivity. All right. Now, you might be recognizing the stereo part and cringing because of stereoisomers, but it comes from the same idea, is that when we add a group, which bond type do we choose? Which bond type do we choose? Okay. And what you're going to see is that when we add things to the carbon-carbon double bond, we're going to be degrading it into a carbon-carbon single bond. And what we're going to see is that, sometimes things get put onto the wedge, whereas sometimes they're put onto the dash. All right. And so this is stereoselectivity. Stereoselectivity means, okay, is it always going to be a wedge and a dash? Or is it always going to be wedge and wedge or dash and dash? So we're talking about those different inevitabilities. And we have a couple of different vocab words to talk about it. We have the word syn, we have the word anti, and then I like to say both, you know. And then there's technically another one where we could talk about not applicable. All right. Uh, and we'll see why in a second why this is important. Basically, all you need to know for syn and anti in both up to this point, we'll come back to not applicable in a second, is that syn is you're adding the two things and that they're on the same side. Okay. Now you might be thinking, okay, is this the same thing as cis? It basically is. So we're saying that the two groups had to be both added on the dash, or they're both added on the wedge. Okay. For anti, we're saying the opposite, that if one of them is on the wedge, the other one has to be on the dash. And if the other one's on the dash, the first one is on the wedge, so it's the opposite, anti configuration, anti to each other. Okay. Well, if these things are basically describing cis and trans, then why don't we just say cis and trans? Well, remember that we're describing reactions, right? So we're describing the addition of groups onto it. So we're not describing where they're currently located. We're describing where they get added. So we're describing reactions. So we have to use new reaction type vocabulary. All right. So if you said that, oh, this is a cis reaction, that's wrong. It's a syn reaction because we're adding in two cis bonds. Okay. So the terminology is a little bit specific, but you have to be making sure that you're saying the correct words. So it is a syn reaction that adds cis groups. Okay. Moving on, we have both, and basically what both is just saying is that it doesn't matter. Okay. The relationship between the first thing that gets added and the second thing that gets added does not matter. So it could be wedge wedge, it could be dash dash, it could be wedge dash, dash wedge. We don't care. It could be any of these four combinations. Okay. And this last non-applicable basically is stating is that there's no stereochemistry. Okay. So what we're going to find is that some of these alkene reactions that we're going to be coming about don't actually generate any stereochemistry whatsoever, so we can't even describe stereoselectivity for it. Okay, there's only a few reactions that are like that. The majority of these are going to be pretty straightforward, but you know it is what it is. Last bit about stereoselectivity. What I want you to know is that when we go from the carbon-carbon double bond to the carbon-carbon single bond, we're moving from sp2 hybridized carbons to sp3 hybridized carbons, right? So can we describe wedge and dash on these things? No. No wedge and dash. Let me put this, let me label it like this. No wedges or dashes, okay? However, we can describe things like cis or trans, right? So we can say cis or trans, right? So we do have stereoisomer relationship words to describe. It's just that we can't say wedge or dash, okay? Because there's no 3D aspect to a carbon-carbon double bond, right? It's flat. sp2 hybridized carbon is flat. Likewise, when we get to the carbon-carbon single bond, this is sp3 hybridized. So we can say, if something is a wedge or a dash, right? Can we still say cis or trans? Sure. Can say cis or trans, okay? But wait, didn't you tell me that we can't say that because of this? No, no, no. I said that we can't describe reactions as cis or trans, but we can describe the groups that get added as cis or trans, okay? Once again, it's a little bit confusing, but as we go through them, it's all gonna get cleared up. So with this kind of vocab in mind, we're able to move on to our reactions. And before we do that, I just want to show you how you can study these very, very simply. What you're going to do is you're going to get a flashcard. It kind of took up too much room. Uh, here's the front side, here's the back side. On the front side, you're just going to write the name. And on the back side, you're going to write the generalized reaction. So you're going to see me, I write it like this. Then we're going to have a series of bullet points. And then, maybe at the bottom, you're going to do some practice problems at the bottom. Okay. But this is the setup that you're going to have. You're going to have the name on one side, and you're going to have the generalized reaction on the other with the bullet points that we're going to present. Okay. And by doing this, you're going to come really familiar with how to know the reaction very, very well, but then also explode it out to different examples. Because for this lesson, it's not enough to just know the reaction. You have to know how to identify it. Okay. And that's everything that we're going to be going over today. Cool. So let's take a look at the first reaction. Now, what I'm going to do is I'm going to present them to you in pairs because a lot of them are just, they're very, very similar, but we're changing one thing, okay? And this is where people usually get confused about learning alkene chemistry is that it's very straightforward once you know what the similarities and the differences are, okay? So let's take a look at our first one. Our first one that we're going to talk about is hydrohalogenation. Now, I'm always a big fan of figuring out what these words mean. So in chemistry, what does hydro mean? Now, you might think, okay, hydro is water, and in any other kind of science, you would be right. But in chemistry, hydro refers to hydrogen, okay? If you see something like hydra, hydri, hydre, or even where it's just HYDR, usually those are referring to water, okay? But if you see hydro, then that is hydrogen, okay? Next word is halogen. Well, this one's easy, right? This is just an X. So we're talking about, Cl, Br, and I. And then the last word is ation. And this is something those of you who are really good at Greek will probably know that this is just referring to process. Okay? And so what are we talking about here? We're talking about the hydrogen halogen process. Oh, okay, that makes sense. So the two things that I am adding to my carbon-carbon double bond is a hydrogen and a halogen. And that's what these names tell you. They tell you the exact two things that get added for all of these reactions. So if we take our generalized form, what we see is that we have a carbon-carbon double bond. And what we're going to do is we're going to react it with something called a hydrohalous acid. Or in other words, we're just going to react it with HX. All right. Now, what could this HX be? It could be HCl, it could be HBr, it could be HI, all these different things. And what I want you to know is that the carbon-carbon double bond degrades into a single bond. And we're going to add the hydrogen and the halogen across the carbon-carbon bond. So what did I just say? Well, I said that the carbon-carbon double bond degrades into a carbon-carbon single bond. And then we add a hydrogen and a halogen across the carbon-carbon single bond. And look, that's what happened. The carbon-carbon double bond degraded into a single bond, and we add the halogen and the hydrogen across the carbon-carbon bond. Okay? Some notes about this. All right. First note that I want you to know is the regioselectivity. So which carbon gets what group is Markovnikov. Well, this is all well and good, but we don't know what goes on the more substituted side, right? Because we know, and what I'm going to tell you is that we're always talking about the non-hydrogen thing, okay? So the big, fun, expensive thing that could possibly kill you, in this case, is a halogen, right? So we're saying that the X goes on the more substituted side, whereas the hydrogen goes on, goes on the less substituted side. Okay. You might hear the kind of saying that the rich get richer, in which case we're talking about, a substitution goes on, goes where the more substitutions are. The hydrogen goes where the more hydrogens are. So either one of these things are just describing the same fact. Okay. The stereoselectivity is, in this case, both. Okay, so in this case, it does not matter if the hydrogen goes on a wedge or a dash, and it does not matter if the halogen goes on the wedge or a dash. And we're going to take a look at why those don't matter when we take a look at the mechanism and see how that happens. The last sort of 2 points that I want to tell you is that the product is, we can actually write this over here, the product forms an alkyl halide. Okay. And the last bullet point that we have for this is the mechanism. And this proceeds through a carbocation intermediate. Okay. You're going to see me throughout this lecture doing C+, and that refers to a carbocation. Okay. So again, you can see quite easily how all of this can fit on a flashcard, right? Here is everything that would go on the front. And here's the rest of the stuff that goes on the back, right? So you can use this to help you learn the material, okay? Now, you do not need to know the mechanism in order to do practice problems. So before we even dive into the mechanism, let's just practice, all right? So let's say that we had this compound, and I want to react it with HCl. Well, what I know is that I'm only going to have a potential of 2 places in order to put my hydrogen, my halogen, right? And let me label this, A and B. And what I can say is that, okay, I know that I see HCl, and it's HCl is a hydrohalogenation reaction. And I know that this reaction is Markovnikov, so I can say that, okay, I'm going to degrade my carbon-carbon double bond into a single bond, and I'm going to add my halogen and my hydrogen across the carbon-carbon bond. Okay? So where's the halogen going to go? It's going to go on the more substituted side. And where's the hydrogen going to go? It's going to go on the less substituted side. Okay? Now, I didn't draw in stereochemistry here. Why? Because it doesn't matter. Okay? So this could be on a wedge or a dash. So, maybe I draw this to show that it could be, either a wedge or a dash, but it doesn't matter. Okay? Generally, for when we're talking about these reactions in which the stereochemistry does not matter, we just leave them as our straight lines. The other questions I get all the time about doing these reactions is, you know, does it necessarily matter where I put the halogen? Can I put the halogen here? Can I draw it like that? Sure, totally. As long as you're maintaining good 109.5-degree angles with your, compounds, it does not matter to me where you put them. So could you put it there? Sure. Could you put it where I put it? Sure. Could you put it here? Sure. Okay. Does not matter as long as it's connected to the right carbon. Now, don't do the thing I see people try to sneak away with, and they try to do this. Okay. Do not do that. Okay. That's a terrible angle. Don't try to be sneaky and because you forgot how to do the problem and you're trying to get points. All right. Just draw it correctly. The other thing people ask me all the time is, let's say I put my chlorine here. Do I need to draw my hydrogen? No, right? Because in chemistry, we only need to draw hydrogens on non-carbon, non-hetero atoms, okay? So do you need to draw it here? No, you do not. So either one of these could be correct answers. Okay. Like I said, could you put this on the wedge? Sure. Does not matter because the stereoselectivity is both. So you could put it on the wedge. But generally, like I said, when the stereochemistry does not matter, we just leave it on the straight line. Okay. Let's do another practice problem, shall we? This time, let's say it's this. We're going to react it with HI. And again, we're going to say, okay, well, this is a carbon-carbon double bond. And we know there's only two places where the carbon-carbon double bond can react, right? We only care about those two places. And what we know is that carbon-carbon double bond will get degraded into a single bond. Carbon-carbon double bond gets degraded into a single bond. And we place the H and the I across the carbon-carbon bond. And so it's a Markovnikov reaction. So I will go on the more substituted side, and the halide and the hydrogen will go on the less substituted. Again, does it matter where you draw the I? No, just make sure it's connected to the right carbon. Does it matter if I draw the hydrogen or not? No, it does not. Okay, so don't get confused. And you can see how straightforward these reactions are, right? Once you kind of understand the regioselectivity and the stereoselectivity, it really boils down these reactions. Okay, let's take a look at the mechanism. Okay, the mechanism is a carbocation intermediate. Okay. Oh, actually, before we go into that, let's do one more practice problem. Let's say that we have this compound reacted with HBr. We know we have two carbons that we care about. So let's figure out what the answer is going to be. Well, we know that the carbon-carbon double bond is going to degrade into a single bond, right? And we're going to be distributing that H and Br across the carbon-carbon bond. It's a Markovnikov reaction, so the Br is going to go in the more substituted side, but which side is more substituted? But if we look at A is monosubstituted, right? It only has one substitution, whereas B is also monosubstituted, okay? Well, B has the longer tail, so that must mean that it's, the more substituted side. No, no, no. Remember what I said. It doesn't matter the kind of substitution, it only matters that it is substituted, okay? So in this case, this reaction would have two answers. Whoa, there we go. And the two answers would be where the BR, maybe the first time it reacts, we have it on B, and maybe the second time it reacts, it's on A. Okay. And here, would this tail have an effect? Sure. Maybe this is 52% of the time and this is 48% of the time. It's such a small difference that we can't really account for it. Okay. So this is the power of having equally substituted, is that you basically get 50-50 products. Okay. Most teachers try to indicate that there's multiple products for a reaction. Some don't, so you just have to be aware of what you're working with, okay? And if you follow the mantra that we set up here, then you should be able to choose what happens every time correctly. All right, finally, let's take a look at the mechanism. The mechanism is a carbocation intermediate. Okay. Carbocations, as you remember, is a carbon that only makes 3 bonds, or in other words, it is 6 electrons. So let's take a look at this problem that we did up above. Let me erase that. And let's take a look at what happens. Well, what I want you to know is that the carbon-carbon double bond has a partially negative region in it, right? Because we know that it's not a regular bond, it's double the amount of electrons, right? So one bond has a sharing of 2 electrons. Well, this double bond has a sharing of 4 electrons, okay? So this has a slightly negative region, okay? And what we see is that this slightly negative region acts as a nucleophile. Okay? Now, what's a nucleophile, you might be saying? Well, a nucleophile is something that is negatively charged and is seeking out something that is positively charged. And what we notice is that we have this HCl. Okay? Well, chlorine, is a partially negative species. And if this is partially negative, that must mean this hydrogen is partially positive. Okay? And what I want you to know is that this double bond can reach out and grab this hydrogen. Okay? But what happens is that it's almost like a double-handed grab, but one of the carbons is going to win, right? So what we have going on is we have 2 possible solutions that come out of this grab. Okay? The first solution is where this carbon-carbon double bond degrades into a single bond, and the hydrogen ends up on the more substituted side. If the hydrogen ends up over here, that must mean that we have a positive charge over there, which this is the carbocation. All right? The other possibility is where the hydrogen is grabbed by the less substituted side, and we have a positive charge on the more substituted side. And the question becomes, which one of these things forms first? Okay, which one of these things is the greater in concentration? Well, what I want you to see is This carbocation here is a secondary carbocation, whereas this one here is a tertiary carbocation. Okay? The more substituted a carbocation, the more stable. More substituted, more stable. Okay? How do I know this is secondary? Well, I can put a little box around this and I can say, okay, this thing is connected to 2 bonds and that makes it secondary, whereas this guy is connected to 1, 2, 3, and that makes it tertiary. Okay? So once again, primary is way less stable than secondary, which is way less stable than tertiary. There's even a 0, which means that we have a carbon that's connected to only hydrogens and is very, very, very unstable. Okay? Carbocations will always form the more stable one first, which means that carbocations always form the more substituted form first. So, out of these two potential options, which are very valid options, which one is the only one that forms? The tertiary carbocation. Okay? This is why this reaction is Markovnikov, okay? Because the hydrogen is always put on the less substituted side because that'll make a more substituted carbocation, okay? So the Markovnikov ability for this basically says that because this is a carbocation intermediate, we have to put the hydrogen on the less substituted side, so the carbocation goes on the more substituted side. One more time. The carbocation intermediate states that because the out of the 2 carbons that we choose, we put the hydrogen on the less substituted side because that will make a carbocation on the more substituted side. Okay? From here, what do we notice? Well, what we see is that leftover chlorine that was kind of just hanging around now has a full negative charge. Okay? It got the electrons from its hydrogen body and now is a full negative charge. And is this going to just hang around and be like, oh, this is so nice, I'm full negative? No, it's going to hunt. It's going to hunt directly for that positive carbocation. And what we see in the final step is we have that hydrogen on the less substituted side, that hydrogen on the less substituted side and that chlorine on the more substituted side. Okay? 2 steps. First step, hydrogen addition. Second step, chloride attack. Okay? First step, hydrogen addition. Second step, chlorine nucleophilic attack. Okay? Very straightforward. And what we're going to see is that other reactions that proceed through a carbocation are going to be exactly the same. And this is where I want you to know that this is where the similarities come from. Okay? Without further ado, let's jump into our second reaction. This reaction is called acid catalyzed hydration. Okay. And before we even dive into this, we can kind of get a sense of what these different parts of the name mean. So when we talk about acid, acid means an excess of H plus. Okay. So we're talking about something where we have to add some sort of H plus donor. Okay. Why do we do that? Because it speeds up the rate of the reaction. Could it happen on its own? Sure. Could hydration happen on its own? Totally. But by adding an acid, we make it faster. Okay. Hydra, as we said, refers to water. Okay. And ation again means process. So we're talking about the water process, but we're speeding it up with acid. Now, I told you before that we need to have 2 things that are added in order for us to have an alkene reaction. Well, if we write water kind of in this way, what we can see is that we really have two parts. We have a hydrogen part and we have an alcohol part, okay? Or a hydroxy part, I should say, is a more correct term, okay? And so this is the two things that we're adding. We're going to be adding a hydrogen and we're going to be adding an OH, okay? The generalized form of the reaction is that we have a carbon-carbon double bond. We're going to be adding, obviously, we're going to be adding water, right? And then we need some sort of acid, so we could add H2SO4. We could add HNO3, okay? Or in general, we could just have some sort of H plus, you know? We don't necessarily know where that H plus comes from, but, you know, we said that it's there. Or alternatively, we can write H3O plus, right? Any of these things mean the same thing, okay? And these all point to having uh, acid catalyzed hydration, all right? What's the process? Well, we're going to be degrading that carbon-carbon double bond into a single bond. And we're going to be adding that H and OH across the carbon-carbon bond, okay? We're going to degrade that carbon-carbon double bond into a single bond, and we're going to be adding that H and OH across the carbon-carbon bond. What's our bullet points? Well, our bullet points is the regio selectivity. Sometimes you're going to see me put regiochemistry. It means the same thing. The regio selectivity is Markovnikov as well. Okay. What does this mean? Well, it means that the OH goes on the more substituted side. And it means that the hydrogen on the less substituted side. Okay. The stereoselectivity is, again, both. Okay. So it does not matter if it's on the wedge, the dash, wedge dash, wedge wedge, dash dash. It does not matter. Okay. So the stereoselectivity is not hindered at all. Okay. Now you might be guessing, well, why is the stereoselectivity not hindered? And once again, we see that the mechanism is a carbocation intermediate. Okay. The product here is just a regular old alcohol. Cool. So we don't need to know the mechanism in order to do practice. So we can take a look at, you know, our good old favorite friend here. And, you know, we can react this with, let's say, H2O in the presence of sulfuric acid. All right. And we know that this is a Markovnikov reaction, so we're going to be degrading that carbon-carbon double bond into a single bond. And since it's Markovnikov, we're going to be putting the OH on the more substituted side and the H on the less substituted side. Okay? Notice the parallels between this and hydrohalogenation. Okay? They're very, very similar. They're pairs. Okay? It's very, very, very straightforward. Okay? I don't really want to spend a lot of time doing practice. I want to spend more time just talking about through the notes. There's tons of practice out there that you can go and get. So let's take a look at the mechanism. And once again, it's a carbocation intermediate. Now, what I want you to know is that carbocation, whenever we're working with acid, we're always going to be adding this extra workup step, okay? And the workup step can kind of happen in a few different places, but for all intents and purposes, it's going to be very common. What you're going to see is that we're going to be usually removing a proton at some point. Sometimes we add one in, but usually we're going to be removing something at some point. Okay? So let's take a look at our reaction. So let's say that we are starting with this compound. And what I want you to know is that what happens is we know that based on our last reaction, that what happens in the first step is that the hydrogen is added, right? So the first step means that we have to have hydrogen addition, okay? Well, where is that hydrogen coming from? It's coming from the solution, okay? Where did this solution proton, the solution H plus come from? Well, it's probably come from the acid, right? So we have H2SO4. And what this does is that this reacts and dissociates into H plus and HSO4 minus. Okay. Now, sometimes you might be, your teachers might draw this as, it comes from the, a water molecule, it comes from a couple of different places. But for all intents and purposes, all that we care about is that this double bond is reaching out and grabbing a hydrogen from some source. Okay. you know, could you have it reach out and maybe it grabs it from a H3O plus? Totally, totally, totally. Okay. But for simplicity, I'm just going to draw it from the H plus. Okay. From here, what happens, as we know, we have two possible answers for where our H plus can go. Either it gets added to the more substituted side and we get a carbocation, it gets added to the more substituted side and we get a carbocation on the less substituted, or it adds to the less substituted and the carbocation goes on the more. And like I said, these are both totally valid options, but which one is going to get chosen? Oh, it's going to be this more substituted carbocation. Why? Because it is more stable. All right. Now, at this stage, if we remember, the negative chloride ion would have come in and attacked it. But this leftover sulfite, possibly. I don't think so. This leftover sulfuric acid moiety isn't going to jump in and do that. Okay, this thing is stable enough. It's not really interested. What is interested is the water. Okay, and what's going to happen is that this water is partially negative here, and it's going to run in and it's going to grab that spot right there. And we're going to have the full addition of the water molecule. Boop, 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 boop. Just like this, right? No, all right? This oxygen here has two hydrogens. We can't just suddenly drop one, right? We have to show where it went. And so what happens is that this water adds in as a full water molecule, and we have to spend an additional step removing that that hydrogen. Okay, so what happens from here is that some sort of base has to come in and grab that hydrogen. Now, what could that base be? Well, most often and most likely, it's going to be another water molecule. Okay. All right. This is the most likely option. And what that means is that we're going to form that H3O plus, which then is going to which is going to then donate to the alkene. And this is the sped up process of it. Okay. We add a little bit of acid to generate our first H3O pluses, but then it generates itself over time and we cause the reaction to speed up over time. Okay. This is why it's an acid catalyzed reaction. Okay. And so this is how we get to our final structure of having that H add in on one side and the OH adding on the other. All right. This is how we get to our alcohol product. Cool. Cool, cool, cool. What are the similarities between these two reactions? Well, they both start off with this hydrogen addition, then a nucleophilic attack, and then this acid catalyzed hydration just has an extra deprotonation step. Okay? Hydrogen addition, nucleophilic attack, deprotonation. Hydrogen addition, nucleophilic attack, deprotonation. Cool. Cool, cool, cool. Let's take a look at a quick variation on this. Sometimes this is described as another reaction, but what I want to tell you is that it's really the same thing. Okay, don't get confused. The reaction is called acid catalyzed alkoxylation. Acid catalyzed alkoxylation. Okay. Once again, we can go through this and we can say acid is H plus, catalyzed means sped up. Alkoxies are things where you have that RO group. Okay, so we're talking about like an ether. Okay, and what we know, of course, is this. Okay, so once again, this alkoxy group, well, this can be really written as ROH. Okay, and that's the two things that we're adding, a hydrogen and this alkoxy group. Okay, and so just to show you how similar these reactions are and like what these come from is in our above reaction, we had it so that way we reacted our alkene with water and an acid, and we ended up with an alcohol, right? So we added in this. What acid catalyzed alkoxylation is that instead of adding water, we're going to add an alcohol. Still going to use acid. And what we see happen in this case is that instead of adding H and OH, we're now going to add the H and the alkoxy group. Okay? Same reaction bullet points. Both are Markovnikov, both proceed through the carbocation intermediate, both are, their stereoselectivity is both, okay? Or it does not matter in a way, okay? And the product that we make is an ether, okay? Same reaction, all right? But we're just slightly changing what happens, okay? So don't get confused. All right. With that, that is our first pair. So our first pair was hydrohalogenation and acid catalyzed hydration. And then we talked briefly about this alkoxylation, variant on the hydration reaction. Our next pair, very, very, very good reactions, is halogenation and halohydronation. Halogenation. Well, what we know is that halogen refers to halogen, and ation is the process, right? Well, this is an alkene reaction, right? So we need to have two things. Well, what's the second thing? It's going to be X2, okay? So we're adding a halogen and a halogen. The generalized reaction is we have a carbon-carbon double bond. We're going to be reacting it with just a regular, bubbling in some halogen. We're talking about Cl2, Br2, I2, all these things. And what happens is we degrade that carbon-carbon double bond into a single bond, and we're going to be adding X and X across the carbon-carbon bond. Notice how I drew these, okay? That should give you some idea about the relationship between what these are, okay? So again, what happened, we're degrading that carbon-carbon double bond into a single bond, and we're adding X and X across the carbon-carbon bond. Degrading double bond to single bond, adding X and X. What's our bullet points? Well, our regioselectivity what do we think? Well, in this case, it's not applicable. The most substituted carbon and the less substituted carbon are getting the same group, right? So we can't say this is Markovnikov or not because they get the same thing, right? Technically, you could say this is a Markovnikov reaction, or is it Markovnikov? I believe it would be if we could talk about it, but for all intents and purposes, they're getting the same thing. We don't care, right? The more and the less substituted carbon are getting the same thing. The stereoselectivity, though, is very exact, and it is anti only, okay? So both of them are wedge dash or dash wedge, okay? And that relationship is fixed, all right? The reaction mechanism proceeds through something called a cyclic polonium ion. I abbreviate it as CHI. And this seems like a really complicated thing, but let's go through it and let's talk about it. So what's cyclic mean? Well, cyclic means a ring. Halo refers to a halogen. And what does this ending "ium" refer to? What is the ending "ium"? Where have we seen that before? Well, this is referring to a positive charge. And that makes sense because we're talking about an ion, right? So we're talking about a positive charge. Okay? So we're talking about a ring which has a halogen in it, and the halogen contains the positive charge. Okay? This might seem a little bit weird right now, but when we go through it, it'll make sense. Okay? And the product that we're going to be describing is something called a dihalide. All right. Now, you don't need to know the mechanism in order to do practice. So, let's say that we have, this guy here. We're going to be reacting it with Br2. Well, we know that the carbon-carbon double bond is going to be degrading into a single bond. And we're going to be adding Br and Br across the carbon-carbon bond. And so we get a Br here and a Br there. Now, does it matter which one gets wedge and which one gets dash? Yes, it does. Okay. So, sorry, it does not. My bad. It does not matter which one gets wedge and which one gets dash. Okay, so there would be two stereo products. All right, and if you did the RNS on this, you'd be able to determine what kind of stereoisomers these are. I'm not going to reveal it because you guys should be able to figure it out. But kind of think about what's happening. Is everything changing? Well, what kind of isomer would that be? Hint, hint. Stuff like that. Now, if you do these as your products, you get, I give you 80% of the points. I wouldn't give you full points. And the reason for that is because you can't have a wedge and then not affect this other bond. Okay. So if the BR becomes a wedge, then our methyl group becomes a dash. Same thing. We have to change this methyl group and change it to the wedge. Okay. So you can't just place something on a dash or wedge and not affect what else might be bonded to that carbon. Okay. Two stereo bonds, two in plane bonds. Okay. Let's do another one on our good old friend, this guy. And let's find out what happens when we react him with chlorine. And again, what we're going to end up with is two products. All right. So to degrade the carbon-carbon double bond into a single bond, and we are going to be getting Cl, maybe this one is on the dash, maybe this one is on the wedge, maybe now it's on the dash, and this one's on the wedge. All right, two products, two stereoisomers. Now, sometimes you'll see people would just put this, and what that means is that it's you draw one product, but then you're showing that there is the stereoisomer that goes as well. Okay, depending on what your teacher allows you to do, some people allow it to happen, some people don't. Okay, let's take a look at the mechanism. Now, the mechanism is a little bit wonky, but hopefully we'll be able to kind of talk through it, and it'll be really, really simple. Okay. Here is our setup, and I think we were talking about chlorines, so let's do chlorines. All right. So we know that there is a partially negative region in the middle of this bond, right? It has a higher electron density. It's going to be partially negative. What we know in here is that which is more electronegative, chlorine or chlorine? Well, they're going to be exactly the same, right? They're the same atom. So what happens is that spontaneously, one of them will collect more of the electron than the other one, and it will slightly become negative. And the other one will become slightly more positive. Okay? And what we set up is we set up a little bit of a dipole. And what happens is that in that instant, this carbon-carbon double bond can react and grab one of these chlorines. That will relieve the other chlorine from its bond. And what I want you to know is that unlike the other reactions where only one of these carbons is going to win, right? One of them has to get the hydrogen. What happens is that it's almost like it's a double-handed grab. Let me show you a cartoon of what's going to happen. Is that what happens is both of these carbons come out and grab this chlorine at the same time. Kick off that chlorine. And so what forms out of this is this triangle with the chlorine. Okay, so let me draw this down below. Right, so I drew the chlorines down here. So here is our bond with the chlorine kind of at the top of this bond. Okay, this chlorine will now have a full-blown positive charge. Okay. And what I want you to know is that this is a cyclic chlorinium ion. Oh, didn't we already learn about this? We did. We called it, though, the cyclic polonium ion. Okay, and that's what the intermediate is that we have this ringed up uh, chlorine, and it has a positive charge. Okay, looks a little bit weird. People don't really believe me when I say this thing exists, but it does. Okay, now this other chlorine that got kicked off isn't dicking around. All right, it's still there. Okay, but the question now is it going to approach from, we know that one of these carbons is more stable and is going to be the nucleophilic attack, right? We know that this chlorine is really going to be attacking this more substituted carbon. The question is it going to come from the top or the bottom, all right? So let's take a look at a couple of the setup of what it's going to be. I want you to imagine that we kind of have like a little plane going on, okay? And here's our two carbons. What happened is that maybe our carbons formed their cyclic polonium ion. Maybe this is on the bottom. Okay. So maybe to accurately draw what's going on, maybe I'll draw this cyclic polonium bond on the dash. Now, if you notice, there's no reason why this chlorine has to form on the dash, right? It could just as easily have formed on the wedge, right? Totally. But what I want you to notice is that this chlorine that's now coming, okay? Imagine it's a plane, you know. It is a plane, okay? And it wants to fly the route that is going to give it the least resistance, okay? And what we notice is that one of these sides of the molecule is more hindered than the other one, right? And which side is more hindered? The dash side or the wedge side? Well, obviously the side with the chlorine on is going to be more hindered, so the plane is going to go from the other angle. And so our chlorine, our second one that got popped off, is going to be coming from the opposite angle to where the cyclic polonium ion has formed. What this is going to do is that it's going to relieve the bond between the more substituted side chlorine and the chlorine, and it's going to kick it over to the other carbon. And so what we have going on is we have this chlorine, this original chlorine on the dash on the less substituted side, and we have the new aeroplane chlorine on the wedge on the other side. And this is why we have an anti stereoselectivity, because the chlorine will always come to the opposite side of the cyclic polonium intermediate. Okay? It will always, always, always come from the other side as the cyclic polonium intermediate. Okay? Now, same thing that we had described. What happens if this instead had the cyclic polonium intermediate had formed on the wedge? Oops. Let me draw it like. What happens if it had formed on the wedge? You know what I'm trying to draw, two wedges. Then the other negative chlorine would just come in from the other side and it would come in on the dash. Okay, so it comes to the opposite side. And this is what generates a wedge and a dash bond. And it's also why it doesn't, at least for this molecule, there's no reason for why one forms over the other. Okay. The next video we prepare will be when we have something called a stereochemical director, in which, okay, the cyclic polonium is forced to go on one side, which means that the we're forcing only one variation of the wedge and dash. Okay, but for this molecule and for what we have to know right now, it does not matter if it comes on the wedge or the dash for which one, because we get both answers. Okay, we get both stereoisomers. Cool. Once again, just to walk through what this mechanism was that we had this electrophilic addition of the chlorine, which formed this two-handed grab on the chlorine, which caused the cyclic colonium intermediate to form on one side. And then because the chlorine is so large, the other chlorine will, will approach from the opposite side to the cyclic colonium intermediate and will uh, form the opposite bond type on the more substituted carbon. Very nice. Now, the next reaction, once again, is going to be paired to this halogenation reaction. And because of that, let's just take a look at how similar they are. Well, this one is called halohydrination. All right. And I'm a big fan of breaking down the words. So halo, as we know, refers to a halogen. Hydri is referring to water. And ation is referring to process. So what are the two things that we're adding? Well, we're adding a halogen and we're adding a water. Now, what I want you to know is that we're really adding the OH. Okay? If we look at a generalized reaction, what are we going to see? Well, I told you that it was something similar, right? So what's going to happen is we're going to be adding a halogen and we're going to be adding water. So we need to have these two things in order for it to for the reaction to work. And we're going to degrade that carbon-carbon double bond into a single bond. And we're going to add the halogen and the OH across the carbon-carbon double bond. Degrade the carbon-carbon double bond into a single bond, add the halogen and the OH across the carbon-carbon bond. All right. Some bullet points about this. Well, not surprisingly, the regio, or I should say surprisingly, will the regioselectivity in this case matter? And now that we have two different things, of course it matters. And this is a Markovnikov reaction, where the OH goes on the more substituted side and the X goes on the less substituted side. Now, that should make sense, right? Because whatever added first in all the reactions that we've gone through so far have all gone on the less substituted side, where the thing that came in second had always gone on the more substituted side. So this all plays in again to that idea about carbocation stability and more substituted, more stable, all these different avenues of what we're talking about, okay? Our stereoselectivity in this case, again, is anti. And our mechanism is, again, the cyclic colonium intermediate. The product that we form is something called a halohydrin. Okay? So, we could say that this is the halohydrin process, but it's better to just break it down and say this is the halogen water compound or the halogen water process. Okay? To dive into the mechanism, just so that way I can show you what it looks like, because it's really good to compare what's going on, is what we have going on is we have two things in our solution. We have our Cl, our Cl2, and we have our water, okay? all of these things are just kind of sticking around in the solution. They're all hanging around and they're kind of waiting for something big to happen. Okay. So just to kind of use the same sort of colors as before, let's take a look at what's going on. Well, the charge analysis tells us that we know that this thing is partially negative. We know this oxygen is partially negative. We know that one of these chlorines is going to be partially negative and one of these hydrogens, or one of these chlorines rather, is going to be positive. All right. So what's going to add? Well, what's going to happen is we're going to have this uh, double bond reach out and grab this chlorine, which is going to kick off the other chlorine. And we're going to form that cyclic colonium intermediate. Whoa, that was terribly drawn. It's going to form that nice two-handed grab. You know, and maybe this time I want it to form on the wedge. You know, I'm in charge, I'm drawing, I can say what happens and what does not. All right. And so what happens is we have two species that are left over. We have this chloride ion and we have this water. And both of them are negative, right? And so the question becomes, well, which one is going to go and attack? And surprisingly, that the chloride is stable versus this water is more likely to go in and attack the more substituted carbon. Now, the question is, well, why does this thing have a negative charge, but it's less nucleophilic than the water? Okay. And the reason has to do with, look, it's full up on electrons. Okay. So it has a full octet. So it's not really looking to react, even though that there is a possibility. So essentially what it is that this oxygen is more hungry to react, comes in, does the attack, kicks off the bond between the cyclic colonium intermediate, which I forgot to draw as a positive charge, comes in, attacks a more substituted carbon, kicks off the cyclic colonium intermediate, and our product is going to have the water on the less substituted side. And remember, it adds as a full unit, okay? We can't just suddenly get rid of the other hydrogen just because we want to, okay? And we're going to be getting the chlorine on the less substituted side, and they're anti to each other, okay? Or I should say they're trans to each other, all right? And just like before in that other reaction we did with water, what's our last step going to be? Well, it's going to be some sort of deprotonation. And what could the deprotonation be from? Probably it's from another water. But some sort of base is coming in and grabbing that hydrogen. Okay. Could it be the chlorine? Could be. Could it be something else? Very well. But in general, some sort of base has to come along, deprotonate that OH group. And so we are left with our final product. Okay. Now, like I said, does it matter which, does it matter that this OH is on the dash and the chlorine is on the wedge, or could it be the reverse? Very well could be, okay? Because there's nothing telling me which side that this cyclic colonium intermediate has to form on first, okay? So either one is just as valid, all right? So we're going to have two products, two stereoisomers, all right? And like I said, is that, just like before when we had water, we're going to have that extra deprotonation step. Just like when we had hydrohalogenation, we did the same mechanism, but we added water, so we have an extra deprotonation step, right? So you can see the parallels between all these mechanisms, right? That You learn one mechanism and then you learn the variation on it. And that's how you should approach these reactions. Okay. The last one that I want to go through for this video is uh, one that does not go in a pair. Okay. So just to recap what we've gone through so far is that our first pair was hydrohalogenation, which got paired with that acid catalyzed hydration. Our second pair was halogenation, which got paired with halohydronation. And the last reaction that we're going to be looking at right now is hydroboration oxidation. All right. Now, just like how we said that these ones are very similar to each other, and these ones are very similar to each other, what I want you to know is that acid catalyzed hydration and hydroboration oxidation are opposites. Okay? So what that means is that in this, we put the OH on the more substituted side. In this one, we're going to put it on the less substituted side. Okay? So there's a little sneak peek. So let's go through and let's talk about this new one that's come out. All right. Hydroboration oxidation. Obviously, we know that hydro refers to hydrogen. Bor actually refers to boron, which is the chemical symbol B. And then, of course, we know that ation is process. And then a dash refers to a second step. Okay. Now, I don't mean that like all of our reactions that we've had so far, they've had intermediate second steps, but I mean that you could do hydroboration, leave it on the shelf for 30 years, and then come back and do the oxidation. Whereas everything else is that once you get the ball rolling, it has to proceed. All right. So these are two separate different processes, two separate different reactions that we're pairing together. Okay. Oxidation kind of it can be described in two ways. Actually, well, the best way is to describe it like this: is that we're saying there's more bonds to oxygen. All right, more bonds to oxygen. All right. So what's the overall reaction? Well, we're doing this hydrogen boron process. Then we're letting it react completely, and then we're going to do this oxidation process where we're adding more bonds to oxygen. Okay. Let's take a look at the generalized reaction. I'm just going to erase this so I have more room. We have a carbon-carbon double bond that we're going to set up. And like I said, that these are two separate processes. So in the first step, we're going to be adding BH3. And in the second step, we're going to be adding H2O2 with sodium hydroxide. Now you might see other reactants depending on your teacher or where you look. You might see an acid, you might see a different kind of base. It does not matter as long as you have hydrogen peroxide and you have sodium hydroxide or some sort of base. Okay, so you need to have this and you need to have some sort of base. Okay, this will stay the same, but the base might change, and you might change to different things. Sometimes people add water to the step. It doesn't really matter, but you need to have these two things. Okay. What's going to happen is we're going to be degrading that carbon-carbon single bond into, or carbon-carbon double bond into a carbon-carbon single bond. And we're going to be adding OH and H across the carbon-carbon bond. Okay, degrade that carbon-carbon double bond into a single bond, and we're going to be adding OH and H across the carbon-carbon bond. Okay, what are our bullet points on this? Well, our regioselectivity is anti-Markovnikov. It's the opposite to Markovnikov. So now we're getting the hydrogen on the more substituted side. And now we're getting the OH on the less substituted side. Okay. Our stereoselectivity for our previous reaction was both, right? It did not matter. Whereas here, it's now syn. Okay? Where both the OH and the H must be on the wedge, or they both must be on the dash. Okay? Our mechanism here is in 2 steps. The first step is this borane concerted addition. And the second step is an oxidation. All right. And then finally, our product here is an alcohol. All right. Now, with that in mind, we can let's compare 2 reactions, and then we'll take a look at the mechanism. The kind of first step of the mechanism. We'll talk through it. Let's say that we have this, and reacting through this pathway, we're going to be adding H3O plus, and through this pathway, we're going to be adding borane in the first step, and in the second step, we're going to be using H2O2, H2O with sodium hydroxide. All right, now let's figure out what our products would be. Well, we know that based on what we've done before, that this is acid catalyzed hydration. But wait, where's the acid? Well, we're talking about H3O plus, right? Which is the acid, conjugate acid of water. And so what we know is that this carbon-carbon double bond will degrade into a single bond. And we're going to be adding H and OH across the carbon-carbon bond. And OH is going to go on the more substituted side. For this reaction over here, what's going to happen is we know that we're going to be adding an OH and an H, but now we're going to be shifting what's going on. All right. And so now what happens is that the OH is going to end up on the less substituted side. So they're opposites of each other. Okay. Now you might be wondering, well, what happens to this BH3? Okay. What happens to it that it just suddenly disappears, right? And what I want to tell you is that we add the boron, but what happens is that the oxygen in the hydrogen peroxide replaces it. Okay, so we do add this in, but then we kick it off and we replace it with an oxygen, which is where we're adding that hydrogen, more bonds to oxygen, I should say. Okay, let's take a look at the mechanism. So let's use a really simple reactant, just so that way we can fit things in. And based on just even before we know we do the mechanism, we know that we should expect an OH here, right? Because it'll go on the less substituted side. And uh, let's take a look at what happens. Well, in the first step, we know that we're adding in BH3, right? And what I want you to know is that BH3 is like this. It's this boron that has 3 hydrogens on it, okay? Let me actually draw this in the correct position, where we're kind of hovering this triborane above our bond, okay? And so what happens is that we know that this boron is flat, okay? It is sp2 hybridized. It is a flat molecule. And what happens is, just like an airplane, it comes in and it kind of hovers above our double bond, right? And this is the interesting thing that happens. We know that this is partially negative, right? And our boron is partially, how do I want to put this? We know that this is partially negative. And the question becomes, well, uh, what is the charges on the hydrogen and the boron? Okay. Well, if we look, boron actually is more electropositive, or we could say it's less electronegative than hydrogen. So what's happening is that this hydrogen is more negative than the boron. Now, what I want you to know is that this is the only instant of where hydrogen has been the negative thing in any of our reactions. Okay? And so when we look previously, where have all of our negative things ended up? Our negative things ended up on the more substituted side. Did I draw it here? No, I drew it there. Our negative things added up on the more substituted side. Our negative things, negative things ended up on the more substituted side, right? So it makes sense that since this hydrogen is more negative than the boron, it's going to end up on the more substituted side, okay? And what happens is that all at once, we get this funky little box uh, addition going on, okay? So to draw what happens, we put some brackets, stuff like that. Here's our molecule. Here's our hydrogen with the partially negative hydrogen hovering over the more substituted side. What happens is that we end up getting this kind of box intermediate, okay? Where we're starting to form these bonds between the hydrogen and the boron. We're starting to degrade this bond between the hydrogen and the boron. And that double bond is also starting to degrade, okay? So we have this little box going on. And what happens is that this intermediate eventually turns into, our hydrogen and our boron are coming down, they're landing like an airplane. And what happens is we end up with the hydrogen on the more substituted side and our boron on the less substituted side. Okay? Notice and look how that happened. And make sure that this makes sense to you, that, well, why did the hydrogen end up on the more substituted side? Why did it end up the opposite to everything that we've seen so far? It's because it is actually the negative thing in this first step of the reaction, okay? And this is the end for the first step, all right? This is the total end of, what the role of BH3 does. BH3 is a way to put the hydrogen on the more substituted side, okay? What I want you to know, and what I'm not going to go through in this video because a lot of professors don't really talk about it, is that the H2O2 and the NaOH, what this does is they convert this BH2 into an OH. Okay, so they focus solely on this BH2, which ends up putting this hydrogen on the more substituted side and this OH on the less substituted. Okay, so this is how we end up getting this reaction to take place the way we want, is that we put the boron on the less substituted side and then replace it with the oxygen in the hydrogen peroxide, so we end up getting the product that we want. All right, make you know this is a really, really big concept, and it's something that I see a lot of professors talk about. This idea of, well, why is this anti-Markovnikov? And it has to do with the charges on the boron. Okay. To talk about one thing that is kind of important is, well, what happens if you just do only the first step? What are you left with, right? Because I told you that these are two separate processes that you could do the first step and leave it alone for 30 years and nothing would happen, right? Well, what happens is we know that we got to this stage, right? We know that we're here. And for simplicity's sake, I'm just going to erase this so that way we're only looking at the boron. Okay. And what I want you to know is that these two other hydrogens that are on the boron can still react, right? So we still have another possibility for this boron to be put on the less substituted side of another alkene. So, maybe we have another alkene comes along. And same thing here is that these things can react with this boron hydrogen. And now what we have going on is we have this boron in the middle, and now it's connected to of our uh, our alkanes, okay, or two of our R groups. And same thing, we have another of these hydrogens, so we could get another one of these double bonds to come in and react. So again, we end up forming the boron on the less substituted side, the hydrogen on the more substituted side. And what comes out of this is something called a triborane, okay? Where we have this boron in the middle, and it's connected to three variations of our alkene. Okay, so what's the ratio of BH3 to alkene? Well, it's a 3-to-1 ratio, right? That we only need one boron to handle 3 of these alkenes. So if you only do BH3, if you only do the first step, you have to draw the triborane. Okay? Because we're not giving it any oxygen to work up with. Okay? We're not giving it anything to form an alcohol. Now, as soon as you give it that H2O2 and NaOH, as soon as after 30 years, you're like, oh yeah, I should probably react this finally. What happens is that you get 3 of the alcohol that we expect. Okay. All right. You basically cut every single one of these bonds and you put the OH where the cut was. Okay. So if you only do the first step, you end up at the triborane. If you then work it up, then you end up at the alcohol. And then this is a 3-to-3 ratio or a 1-to-1, so which is why we talk about it. Okay. So just to recap what's going on, that we put the boron on the less substituted side because it is slightly positive. Then when we do the workup, we're going to replace it with this oxygen from the hydrogen peroxide, which will give us an alcohol on the less substituted side. So the opposite to what we initially learned because the mechanism is slightly different. Okay. Um, Hopefully you're able to understand these and they make sense and everything like that. If not, feel free to reach out to me. There is something that I wanted to show you as well. Um, Let me, nope, this. If you go to tinyurl.com/Gabe tutoring, it will bring you to this Google Drive. Go into second year stuff, then go to MCPHS Orgo, first semester. You'll see this alkene comparison chart. Oh, look, here's all the alkene reactions that we've talked about. And oh, look, there's all the alkyne reactions that you will eventually learn. And oh, look, here's the first five reactions, the first 6 reactions that we've learned. Okay. So use this tool to help you with understanding what's going on. Okay. The reactions are not hard. They're all comparisons. Okay. So as long as you just remember these two are the same, these two are the same. This is a variation on hydration. This is an opposite of hydration. And these two are a pair. You'll be totally fine for the exam. Cool. Cool, cool, cool. If you have any questions, please reach out. And I hope this recorded.